our Lab2 report. I'm Zifan and my partner is Yuhan. There are two parts in this lab. First, experiment. Explore the bandwidth and throughput experiment. This part includes three subparts. The first one is bandwidth delay product experiment, and the second part is bandwidth delay and loss experiment, and the last part is IPerf hint experiment. The second part is security copy, which explores how Linux computers send files securely between each other. I will go through the first part, explore bandwidth and the throughput experiment, and my partner Yuhan will go through the second part, security copy. So let's start with bandwidth delay product experiment. There are 6 more experiments in this part. First, connect Linux computer with 1 gigabit router and find its round-trip delay. So first, we use IP address command to find out the computer IP address, and then use the ping command to ping that founded IP address. The experiment returns the round-trip delay time is 0.92 milliseconds in our experiment, and then we use IPerf to find the UDP's bandwidth, which is 957 Mbps, and the command, also the result is showing in the screenshot. Then we explore the TCP throughput by using the IPerf. The experiment returns the throughput equal to 941 Mbps. Same to the previous. The screenshot shows the command and the return result. Second is latency experiment. Before talking about the result, let's start with the steps. So first, we use the IP address to find the port number of the Ethernet, and then set 100 milliseconds delay in that port, and then we experiment with other 4 delays. So this is our result. As you can see, when latency increase, the round trip time increase, and the TCP throughput decrease. However, the UDP keeps the same. The third part is link speed experiment. There are 2 steps in this experiment. First, using the following command to change the maximum speed of the Ethernet link. And the second step is to do the experiment with 10 Mbps, 100 bps, and 1000 bps. So here is our result. As you can see from the previous result, when the link speed would affect TCP throughput and UDP bandwidth dramatically. However, the average round-trip delay was not influenced largely. The link speed determines the maximum number of the speed computer can be used to send or deliver the package. The higher the speed, quicker the package could be sent. Therefore, TCP throughput and UDP bandwidth would increase. The surprising part was the average round-trip time does not change very much. After experiment, we found our receive and send network buffer size by using following command in the screenshot, and the result was also in the following screenshot. The next part is to explore and do some experiment about change the send and receive window size to 2 MB. Here is how we change the receive and send window size. And then we follow the same steps in the previous part and the parts before the previous part, and we find out some result. And the result was shown in the screenshot. So from the result in the previous slide and in the link speed experiment, we found when we decrease the maximum size of send and receive windows, the RTT increase, the TCP throughput decrease, and UDP's bandwidth decrease. Decreasing the send and window size could cause less byte could be sent or read by the computer. Therefore, it could cause the situation shown in the result. The next experiment is TCP send and receive window experiment, and we use the following command in this slide to change our TCP send and receive window size in both server's part and the client part. And we also do the same experiment in the part before, set the latency, set the link speed, and change the window size. And this is our result in this experiment. And we found out that the link speed, send and receive window size, and the latency could affect the TCP throughput. The higher the link speed, the larger the TCP throughput. The lower the latency, the larger the TCP throughput. The optimal send and receive window size, which can be calculated by the bandwidth and the delay, could return the best TCP throughput. The last part is bandwidth delay product result. In this part, we found the window size theoretically by using following equations. Use bandwidth delay products divided by 8 divided by 1024, and we returns 305 kilobytes for the send and receive window size. And we also run the experiment in that size. We didn't get 100 bps throughput. We believe this is caused by the delay. The delay caused the congestion, and therefore caused the lost packages.
So here's our second part, secure copy. What we are going to do in this part is to copy a file from one device to another one using the secure copy over the SSH connection. So the first thing we did is to set the network at 100 megabytes per second. And the second thing is install OpenSSH server and client package on each device. As I said, we use a security copy over SSH connection, so we have to do that. The third step is create a random file in Yuhan's laptop. We use the dd command. Let's look inside the dd command. After the if part is the input, and we can see the input is some random data. And after the off is the output, and we can see the output is a file named data.bin. And BS is used to set unit of block, and count is used to set the size of the block. So we can see the output is a 200 megabytes file named data.bin. And next step is using the security copy command. We can see the first part after the security copy command is the, let's call it input. And the second part is the output. So we can see that this part is the server's name and server's IP address. And here's the server's directory we are going to copy the file to. Okay, next thing is to look at the throughput we can get using the SCP. It's 2.9 megabytes. We want to see the delay and how delay and window size influence the throughput. So we change the delay and window size. The first picture shows that after we set the delay to 25 milliseconds, we can see the throughput is 300 and over is much lower than before. So the delay influences the throughput a lot, I think. And the second part, we maximum the window size. And we can see the throughput is still 233. The maximum window doesn't work well, which I think because default window size is already big enough, which is close to maximum size. So even if we maximum the window size, we can't get much more buffer size, so we can get much higher throughput. So next thing, inspect the SCP built-in limitation. SCP uses SSH protocol to transfer. SSH has protocol implementation and encryption overhead that based on the amount of CPU processor and memory resources given to that transfer session. The buffers and limited available resources often end up become a bottleneck for network throughput of SCP, especially on long and high bandwidth network links. So question 10, set different packet loss situation. So in this part, we found out the packet loss relationship with the throughput. As we can see from the result chart, along with the packet loss percentage goes up, throughput goes down. It's not very extreme. In this case, if the number of lost packets increase, TCP protocol will resend these packets to ensure nothing is left. That's TCP property. Therefore, for the same size of file, high percentage loss condition will require more time to finish the job, the transfer job, which leads to low throughput. And question number 11, delay and loss between Los Angeles and Switzerland. The distance between these two places is 9,549 kilometers. We can use that to calculate the delay. It's almost 30 milliseconds. The distance is the straight line distance, so the actual delay will be larger than the value we have calculated. The second part is the loss. It's hard to estimate the loss because data we are transferring will get through so many different routers at unpredictable circumstances, like link congestion, bad cable, loose connection, and duplex mismatch. We need more information like what kind of network key we'll use, such as wired or wireless, such as wire for open or closed, something like that. So it's hard to estimate the loss. So that's it. That's the second part.